Welcome. Let's get rocking with problem 5. Now, a homogeneous polynomial show that this equation holds. It should of course hold for each term. So let's just take one term. And the sum of the exponents equals n. And then the left-hand side, we can't write on this, so I'll just have to copy it. This means differentiated by x, y, and z respectively. So we get, this is actually tedious writing. We get y down here, and then y up here is reduced by 1, and then since we multiply by x, it's added by 1 again. So what we get is basically I plus j plus k times f nf. So that's rather trivial. Now b, if k has characteristic 0, show that a point is a non-smooth point on the curve if and only if the gradient at the point vanishes. Give a counterexample if the characteristic is non-vanishing. In what follows, suppose the characteristics of k, for instance, the real numbers or the rational numbers, sure. Now, so what does it mean that we have a non-smooth point? What's a smooth point? That was A. So I thought that was defined by the tangent or the gradient being non-vanishing. So we just have to look up what is a smooth point. I should of course have done this originally. Oh, it says on the bottom of page 9, we say that C is smooth at a point if the two partial derivatives are not both 0. That's the affine space. They don't define it, of course. So what they mean here is probably that they have defined it in the affine space. Now we shall generalize it to projective space. So let's assume we have a point x naught point y naught plus point 1 and want to show that we know that the affine curve has a smooth point. So if we have the equation like this, that's our f tilde. Then we have the f in a affine space. And we know it's a smooth point on this curve. So that means that fx is, oh, they are not both vanishing. So the product is non-vanishing. So it's only derivation with respect to Z we need consider. And then I guess that we should use the one above here. But now let's check. So we need to show that f tilde z at x naught point y naught point 1 is non-vanishing. So we multiply it by z and use the equation above. Now this vanishes because the point lies on the curve. These are not both 0, but of course x naught might be equal to, oh, it's minus both of them. I just have to, well, it's minus, so it's x naught plus y naught might vanish, and then this would vanish. So let's try an example like y equals x That's a lovely line. And the polynomial y minus x is already homogeneous. And we have the smooth point 1.1.1. And the derivative with respect to z does vanish. But this was wrong. One of them must be distinct from 0. So we just, oh man, I've been dumb. We don't need this at all. It's far too complex. So we have to compute f tilde x at x naught, y naught, 0.1. And that's of course equal to fx at x naught, point y naught, isn't it? The z terms are added just to make up the total, and then when set z equals to unity, it vanishes anyway. So going to the affine space here, it's the same, except now the gradient has the same first two coordinates when we go to affine space. So B is obvious, really. But where did I use that we had characteristic and we'll have to find the counterexample to understand where I went wrong. And let work in a space with characteristic 2. The field with just naught and unity. When we differentiate fx equals 2x, which of course equals 0, they have have gradients 0 everywhere, and we have the point 1.1 minus 1. Oh, it's if and only if. I didn't get the only if bit. I only got the if bit. So we have to show one which is non-smooth. So the aha. So now I understand it. It's the other way around. If it's a non-smooth point, then we need to show that so we have shown this. So to show it the other way, we could have one where the derivative with respect to z was non-vanishing, but the derivative with respect to the other two were. So is it possible that these two vanish and this one does not? That could be the case if z was, in our example, 2, the characteristic of the field. So I'm confused at this point, so let's stop.